Full domain-specific model training can be very expensive, costing hundreds of thousands of dollars in GPU hours and very involved training using parametric efficient fine-tuning. A faster and more cost-effective approach is fine-tuning of large language models as retrieval augmented generation, known as RAG or RAG. This video covers RAG use case development within Ai-MicroCloud. This image highlights the end-to-end RAG process where any private unstructured content can be model fine-tuned with any LLM to generate in-context query results using a standard chatbot. In our demonstration, we will be using the Llama 2 LLM from Meta. Ai-MicroCloud brings the AI stack to data, so what you see in this video could be done within AWS, Microsoft Azure, or on-premises in hybrid data center environments. The RAG use case in this video involves loading unstructured documents, creating knowledge context and using them with pre-trained foundational models like Llama 2, or Mistral AI or Databricks MTP, etc. In this video demonstration, we use the Llama 2 13 billion parameter foundational model. Embeddings are created using the unstructured documents, and these vector embeddings are stored in a vector store, for example CongaDB, and are further indexed, say in MongoDB, for faster retrieval. The chat applications can then interact with a fine-tuned model. A fine-tuned model is a foundational model API that utilizes the knowledge context created in this process before constructing responses based on its pre-training on the broader corpus of data. This video covers retrieval augmented generation, also known as RAG, showing use cases that can be built within Ai-MicroCloud. Go to Dataset tab to upload the unstructured documents. Create datasets and provide data set name and description. Select the file to upload. Click on Upload File button to use file that is inside the dataset. As part of our AI Copilot suite, we have created an easy starting point application for rapid embedding creation. This application is also known as a microservice. Resource allocation can be controlled for performance. When larger set of documents have to be handled, development teams can actively see the resource utilization and map GPU and CPU resources to these activities. This improves productivity of the development organization during the embedding creating process. We provide the inputs on Vector Store and Index Store, which are also started as a microservice within the Ai-MicroCloud. We use ChromaDB within the platform, but other vector stores can be imported as microservices with equal ease. Next, we also spawn a Mongo database as our IndexedDB, which will be indexing all the vectors stored in the VectorDB along with related metadata. In a production system, this database could be external to Ai-MicroCloud. After we have spawned the required microservice, we will be opening our embedding creation application in a different tab. Now we need to provide the vector store URL and in-user interface of the embedding, which we can copy by going on to our MicroCloud workspace and picking them up from the microservice tiles. Next, we provide the name for the vector collection, which will be stored inside our VectorDB. The thing to keep in mind is we need to have the name of the vector collection similar to the dataset we had created in the beginning. Next comes the IndexedDB URL, which we will be providing by going on to the MicroCloud and copying OT from the Mongo tile. The data lake URL will be user-specific, which will be provided once the MicroCloud is initially handed over. The username and the AI Data Lake secret key can be collected from the Manage MicroCloud tab as shown. Now we select the file that we just uploaded from the bucket as our knowledge repository for embedding. This example uses Llama 2-13b for creating embeddings. The All Complete pops up on the screen indicates that embeddings are successfully created. Now after the embeddings are created, we spawned a Retrieval microservice that is part of AI Copilot Suite for fine-tuning of the underlying pre-trained Llama 2-13b model. This microservice delivers LLM as a secure API. After the fine-tuning application is spawned, we can start a chatbot application to interact with the LLM. But in this case, the response context comes from the knowledge repository created during the embedding process. As mentioned, we are directing our fine-tuning application to the knowledge repositories using URLs, which allows the application to connect to the collections inside them. After providing the URLs for the knowledge repository, we direct the application to the correct collections and use the chatbot for interactions. In this case, we ask the LLM a question about the financial results of the quarter and receive a response answering the query.